Okay, so this is, as you see in the title, this is my perspective. So we know what the state of the art is to some extent, at least partially. We have the pocket AI, ChatGPT, DeepSeek, and so on. 3 years ago, we didn't know it existed, and nowadays we could not live without. But this is kind of pocket artificial intelligence. There is also the big science. So the Nobel Prize last year to Geoffrey Hinton for his mathematical fundamental contributions to machine learning, but also in chemistry for the use of machine learning and artificial intelligence to tackle problems in, in this case, the unfolding of proteins. So these, they were smart in the Nobel Foundation when they said, let us give one prize to those doing the mathematical, say, foundations of artificial intelligence, but let us also recognize to those that are using this artificial intelligence, the existing artificial intelligence, in the most intelligent manner to tackle the most ambitious challenges of science and technology. And this is how the field is being driven, right? So there is a lot of mathematical background, foundational work, from time to time a breakthrough that helps going to the next stage, and then tackling also more and more ambitious challenges. You know that nowadays there are AI programs funded by OpenAI and other companies to tackle different mathematical problems, like solving the problems of the mathematical Olympiads, or trying to solve some of the millennium problems, like, for instance, Navier-Stokes equations, right? So now that this is occurring, there are some discussions, there are some people that say, well, this is just a bubble, right? So this will pass. So I don't pay attention. I am not interested. I continue doing my, I like finite differences, so I continue doing finite differences, or I like finite elements, I do finite elements, right? I put, more grids, or, I take more corners in my domain because I like regularity theory, so, I take the systems more and more equations, more and more corners on my polygon, that's fine, right? So you can believe it is a bubble or not. Okay, so then the discussion today is how this new field emerged. And then so in the discussion we had before, I asked what was the starting point of artificial intelligence. Someone said in the 50s, right? It could be indeed Second World War, the computer, the emergence of computer, information theory, and so on. This could be the starting point of artificial intelligence. Some other will say, no, it was Gauss and Legendre when they invented least squares. Somehow this was a paradigm shift, because the question was not anymore trying to find the best ordinary differential equation or partial differential equation, like Euler equations for fluids, or Navier-Stokes, or D'Alembert for the vibration of the chord of the guitar, the first model in elasticity. It was not about finding differential equations, but it was more like filling data, right? And some others will say, well, in fact, maybe the first contributor to artificial intelligence was Aristotle, when he said 2,500 years ago that actually what humans should do is to build machines able to do the work they used to do, right? So to be free to do other things. And in that sense, ChatGPT is a very good example. Now you don't need to spend time on translating a text or correcting the typos in a Word document. You can just let it do by the machine, let it done by the machine, and this will be done in a few seconds or minutes, okay? So it's everything about building bridges. So now when you try to explain how this happened, it's not that clear. It was very nonlinear. It's multidisciplinary. There were different contributions, but eventually, once this occurred, this was a paradigm shift, and I don't think this is a bubble. This is a change that will, like a tornado or a tsunami, that will affect everything we do. The way we work, the way we do research, the way we teach, the way we study, also the way we manage our things, because nowadays, you have to deal even with, home-like administration things. You can just let ChatGPT do an Excel page, and many things that we used to do by hand, now this will be done automatically. So I'm sure Aristoteles will be very happy if he will see to which extent we were, keen to follow his advice and develop these tools that are able to do our work so that we can focus on these lectures. So there is electricity, there is heating, there is internet, the video is working, so we can just focus on this communication. So now, when I go to Erlangen, as Ivan said, I'm used to be trained as, functional analysis for partial differential equation, numerical analysis, control theory, inverse problems, maybe technological transfer, the old tradition. And when I go to Erlangen, I realized that there was a lot of interest on topics related to artificial intelligence I didn't know about. But this was the demand, right? So in Erlangen, in the perimeter of the university, we have the Helmholtz, we have the Fraunhofer, we have Siemens, Puma, Adidas, Schaeffler, and all of them seem to be very interested on, kind of new tools that didn't belong to the community, to the folklore to which I belong. So, well, I said to my group members, we should maybe try to explore. And the way you can explore is always from your own side, right? So it's about building bridges, but there are so many possible bridges. There are bridges from every discipline. So what we did was to try to approach the discipline of machine learning from our own understanding. So this is a simulation we have done before, right? Which you will see it belongs classically to control theory, although the application is interesting because you see how 4 dogs, so these blue dots are dogs, so 4 dogs are herding a flock of sheep. So this red square is full of sheep, and these are 4 dogs whose task is to herd this flock of sheep. And this is an application to machine learning, where the task that, in this case, the deep neural network has is to somehow organize the data you see mixed here. You see yellow, green, and purple dots that are all mixed. You have to classify them by their color, by their labels, okay? So these 2 different applications. So you see the first one, 4 dogs, they develop this kind of a strategic dancing motion that is herding the flock of sheep all together towards the northeast, where their arrival point was previously indicated. And this is the deep neural network that is able to take all these dots and bring them to the corresponding destination. So if I didn't say that this was classical control theory and this was machine learning, I could have said, well, this is about something about particle dynamics, complex dynamical systems, interacting particles or something like this, and everyone would have believed. If I ask you about the difference between this video and the video to the right, probably you identify that here there are no dogs, right? So here you see what the dogs are doing. A posteriori, of course this is a numerical simulation. I will not be able to anticipate that this was an optimal strategy for the dogs. This was a numerical simulation. So what we say is we write a dynamical system in which sheep and dog are interacting. So this is a very asymmetric interaction between sheep, because sheep are afraid of the proximity of dogs, and dogs want to get close to sheep. So what here in this asymmetric interaction is occurring is that the dogs are moving in a way that they are building an invisible corridor, diagonal corridor, and then sheep, the intuition of the sheep is that they want to be as far as possible from the 4 dogs. So they are looking at any time this point, which is the farthest away to the 4 dogs. So the 4 dogs are building a polygon, and the sheep are trying to be in the middle, right, in the center. And it's by doing so that they are moving without knowing that they are getting to the destination. So here there are clearly 4 dogs that are playing the role of controls, while here there are no controls. So this is the main difference. Seems to be a control problem, here no control. But in fact, here there are also controls, because if this deep neural network was able to achieve this task of classifying data, is because the parameters of this neural network were previously trained, pre-computed, so that this task will be solved successfully. And when computing these parameters, we are actually solving a control or optimization problem. This was our starting point. And then we said, well, if this is true, then somehow all we know in control theory can be used in order to explain at least partially the success of machine learning. So now how does it work? As I said, it was very much like Gauss and Legendre. It's about just interpolating data. It's just trying to represent data by a function, except that nowadays in neural networks, the function is not a linear function alpha times t plus beta like in classical least square, or a simple parabola that is trying to interpolate a cloud of points. But here functions belong to a much wider class. Basically is any graph. Any graph is a neural network, but in order for a graph to become a neural network, you have to say every node becomes a neuron, and the fact that the node becomes a neuron, this transmutation is achieved by an activation function that can determine whether it's on or off. Again, very much like in control problems, because, you know, like the heating system is based on an on and off principle, so that when the thermostat itself is too cold, the air conditioning or the heating is on, and when, you know, the temperature goes beyond a given threshold, it will be off again. So this kind of bam-bam principle in control theory is what we do here. So in a linear graph in which the connectivity of these nodes, in between these nodes, can be activated, right? Make it more intense or simply avoid it. Here we are not only doing this, but we are also allowing every neuron to decide whether it's on and off. So there are many parameters to be optimized, many more as in the classical least square, but the idea is very much the same as in Gauss and Legendre. You try to match every datum to the corresponding label by just optimizing the parameters. I will explain what that means. So, but then by now, let's say that A, W, and B are just representing all the possible combinatorial, degrees of freedom of this neuron. So you try to make sure that the graph in here is able to guarantee that whenever you plug an X here, what you will get here on the exit is very close to the corresponding label. Now, in the context of machine learning, we face several devils. So one of them is the course of dimensionality, as I was explaining in the previous discussion we had. In ChatGPT 3, not 4, not 5, so ChatGPT 3, a baby version, the number of parameters to be optimized is 175 billion parameters. And here, although the problem looks very nice, quadratic, convex, and so on, is non-convex. Why? Because every neuron is allowed to be on or off, and this is a nonlinear operation that breaks the convexity of the problem, so that in practice we are minimizing a nonlinear, non-convex problem, functional, in a space of dimension 175 billion. So everything in the context of machine learning and artificial intelligence becomes immediately, very rapidly, very high dimensional and non-convex, and therefore technically difficult. So these images are taken from this webpage, 3 blue, 1 brown, that I recommend. I use them also, for instance, in my master's courses, because the principles of machine learning and artificial intelligence are explained through some videos that I find particularly pedagogic. As I was discussing before with you, of course, the success of machine learning and artificial intelligence was the common success of many, many contributors. Some of the ideas that I find particularly intelligent is that, for instance, this idea of next token production, that is a quite simple but fundamental observation, saying, listen, if you give me a piece of text, like in here, in this poem, I can, even though this simply seems to be a passive input, I can extract out of this text a table of inputs and outputs by the simple rule that there is a next word to every previous one. So if you give me the input behold, then there is A as an output, and then if you give me the pair behold A, there is Y as an output. So I can extract labels out of data which in principle don't seem to contain them, okay? So the fact that people were able to put text into Euclidean spaces, extract labels out of passive, say, text and so on, made it possible to apply all these ideas that originate already in the least square formulation of interpolation problems. So now, world changed. Until now, we were told in class, listen, everything in the universe is described by mechanics, and then in mechanics, every phenomena has to be modeled through a PDE, and PDE there are three types, Laplace, heat, and waves. Now the world has changed. PDEs have disappeared, and we try to model the processes we are facing by interpolating the data that is available through these models that are purely artificial or synthetic, okay? So now, how can this work? Actually, when you look to the mathematical foundations of why machine learning works, I already mentioned Gauss and Legendre as those that initiated this idea of interpolating data through ansatz. There are several key contributions. One of them is due to Norbert Wiener, his paper in Tauberian theorems back in 1932. This was a 100 pages article in Annals of Mathematics. It's very much, you know, it was the age of Paley, Wiener, and so on. It was very much a foundational paper in Fourier analysis. But he said something that at that time people maybe considered to be a curiosity, didn't realize how relevant it was. He said the following: give me a Gaussian. You give me a Gaussian G. If you let me translate this Gaussian wherever I wish by choosing the centers of gravity, of course, weighting them through the coefficients W, and you let me combine a packet of them, I can build classes of functions that are dense. Right? So this is a density result. Now the difference in here with respect to classical density results by polynomials or Fourier or finite elements is that the basis functions here are not fixed a priori, because the reference function G is given, but this function can be located wherever you like. So this was the starting point of nonlinear approximation theory. So by this theorem, Norbert Wiener inaugurated the age of nonlinear approximation theory. Okay? So in his theorem, actually not only is true for a Gaussian, what he needs, the proof is just an exercise using Fourier transform. This is a good exercise for a master course, actually. What he needed is that the function G for this approximation theorem is so that its Fourier transform never vanishes. So, you know, Gaussian is a very good candidate because the Fourier transform of the Gaussian is a Gaussian, so it never vanishes. You can apply, you know, Wiener. Okay, so it took, there was a long winter until Cybenko in 89, 57 years later, he said, oh, I can do the same as Wiener, but instead of taking the Gaussian, I can use the sigmoid function here, which is any nice function with asymptotas 0 and 1, transition from 0 to 1. And this is something that people like very much, and then people realized this was the missing piece, because this sigmoid is precisely mimicking this behavior of a neuron, a cell, a node of this graph, to be either off or on, right? And then Cybenko said, but in order to do that, of course, I cannot apply directly Wiener, because the Fourier transform of this function, recall that the Fourier transform of a jump function is the Shannon sinc function, which has many, many zeros. So you cannot apply Wiener directly, but you know, you can do the same under the condition that you add an extra nonlinear parameter on the ansatz, which in this case is the, you know, scaling parameter A, right? And then it's not hard to understand why this is dense, because you see, if you scale this sigmoid function with an A, you stretch, you know, the interface of this sigmoid function becomes a Bam-Bam function, a Heaviside function, a jump function, and therefore when you make linear combination like this, you are building piecewise constant functions, which are the classical simple functions we use in Lebesgue integration theory, for instance, to say simple functions are dense. So of course this is a dense class. Actually, another way in which you can see that this is very much related to classical foundational results that are well known in classical approximation theory, nowadays people have the tendency to replace this sigmoid by this, this is called the ReLU, rectified linear unit. Rectified linear unit is just 0 to the left, linear to the right. And then if you take this function in 1D and you do this kind of operations, you see that this is a finite element P1, classical piecewise linear and continuous functions. We know finite elements are dense, so these functions are of course dense. But now here, this is nonlinear approximation theory again, because the basis functions are not fixed, like we do in finite elements when we fix the grid, but rather they are free because the switching points of these ReLU functions are determined by A and B. Right? If you take this reference sigma function to be, jumping, having this corner at 0, the corner of this function is minus B divided by A. So in here, not only you have the classical finite element functions of numerical analysis, but actually you have all the finite element functions you could get in all possible grids. So of course this is dense. This is actually super dense. There are many ways you can approximate a function out of these assets. And this is not necessarily a good thing, because this leads to the embarrass of choice. While in classical linear approximation theory, the beauty of linear approximation theory is that once you fix the basis and you prove density, then the problem is very easy to handle because the coefficients on the basis are just the projections. Here, this is a nonlinear approximation theory result, and therefore even if you know that there is such a choice of coefficients W, A, and B allowing you to approximate the function, you still have to perform the task of finding them, and this can be very hard because of the lack of convexity. So soon after, people realized that this way of doing by Wiener and Sibenko, that was some kind of static, right? Because you are piling up neurons in one tall column. Maybe it was better to do it gradually in a kind of time-discrete setting, in particular because this will help interpretability. When you think this way, it's very hard to have an intuition of. It's like if you ask a person to coordinate the action of 25 arms simultaneously. I mean, we already have difficulties to handle 2 hands. So if we had 24 arms, we will never be able to do it. But we can, in a time-discrete manner, we know how to alternate actions strategically in order to achieve a goal. And this is how, we move from, very wide and static, shallow neural networks into narrower but deeper neural networks in which gradually, neurons were added layer by layer, very much like in a time-discrete dynamical system. And once you see this, you realize that actually you are getting close to control, because control theory, and this was also one of the contributions of the same Norbert Wiener 16 years later, when he writes the book of Cybernetics, in which he defines cybernetics as the science of control and communication in animals and machines, which could be probably also a good definition for what artificial intelligence is, right? Soon after, there were seminal results, like for instance, this classical result by Kalman, whose proof is elementary, but still, indicates that there is some hope that this kind of ideas can be successful, because in particular, what Kalman says, give me a very complex dynamical system. It could be, all the German society where you have 84 million inhabitants, so you have a vector of 84 million components. There is the possibility of, for instance, generating consensus under the condition that you are able to have a number of influencers that are able to guarantee, that the rank of B, A, B up to, AD minus 1B is full, right? So this is why, for instance, we can drive a car. So the simplest model for a car will be 4-dimensional, but we have two controls only, but we know a car can be driven, although it's not that easy, right? Because if you want to pass the test for the driving permission, very often you need to take a few classes in the auto school, right? Because it's not that easy. Once you learn, it's very easy. It's the same as learning to bike, Once you learn it, you never forget it. But as a kid, it takes a while until you can operate a bike in a stable and efficient manner. So the same here. So building these brackets, the information coded in the rank of this big matrix is precisely what takes a while for humans to learn when you are trying to, learn to bike or learn to drive. Okay? But nowadays, this is well understood, right? And, so this is a very good parking driver, right? So you want to park your car, you can just buy this engine, right, and let it operate. You see, in the hardest possible conditions with all obstacles, as soon as there is some room to find a way of parking the car, this robot is able to do it, right? So this is optimal parking. That's not that easy. Probably for many of us, we will not even be able to park the car in those conditions, and those able to do it certainly will probably have to operate back and forth the system many more times in order to succeed, not to park alone. So this, this robot is able to find the geodesic, right? But well, the geodesic where? I mean, the geodesic for the motion of this car in this territory full of obstacles is very complicated. We have a very bad intuition about what the geometry of this geodesic and this manifold is. Well, the robot is able to find this geodesic. This geodesic, of course, is hidden in the classical maximum principle of Pontryagin, right? Which says, listen, there is an optimal trajectory, and the optimal trajectory can be characterized by these equations. Yes, but nobody is able to compute these equations, the solutions of this equation, right? You can do it numerically, you can approximate it, and then in practice, you have to realize the same task of the computer, but manually, and this is something straightly very, very hard. Actually, it was in the context of control theory when Richard Bellman in the 60s, more or less simultaneous to Kalman, he said, listen, control problems are very easy, right? So you take an n-dimensional control problem, and you want to drive the system from this point to that point. It's very easy. The only thing you need to do is to solve the Hamilton-Jacobi equation. Yeah, but the Hamilton-Jacobi equation is a nonlinear PDE in dimension n. So as the dimension of the problem increases, this is something that even nowadays, with the best, say, understanding of Hamilton-Jacobi-like equations and numerical solvers, we are not able to do. So this is when he said, listen, when tackling these problems, humans face the course of dimensionality. So course of dimensionality, a key concept in the complexity of artificial intelligence, was coined also in the context of control theory. Now, how do we see control theory emerging? It's a little bit like in here. So this is the static ansatz of Sibvenko or Wiener. We move into a time-discrete context, and then we realize, oh, but this time-discrete neural network, deep neural network, in which I'm not piling up all neurons simultaneously, but I am adding one per time step. This is nothing but the time discretization of this differential equation that I will call now neural differential equation. I say this is a neural differential equation because it's inspired in neural networks. And the nonlinearity of this differential equation is the ReLU. Now, the great revolution with respect to classical mechanics is that the differential equation is the same. So this is extremely frustrating, right? We spend all of our lives learning about the difference between, the different equations in mechanics and how, they behave so differently, and then eventually everything is modeled by the same differential equation. So regardless what the dimension of the problem is, the differential equation is the same. And now the only thing you have to do is to choose the coefficients W depending on time, A depending on time, and B depending on time, so that the neural network does what you want to do. And for instance, something that the neural network wants to do is, as I was explaining in the video at the beginning, you give me this class of data in which red and blue are mixed, and you tell me, listen, the blues to the left and the reds to the right. Very much like in a soccer game when, you know, the 22 players jump into the field. In the beginning they are hitting, they are mixed, but, you know, before the game starts, you know, the blues are in one side, the reds are on the other. So somehow the problem now is very much like in classical control, where the challenge was to send a rocket from Earth to the moon, except that now we are not doing it one control strategy per trajectory, but we are willing to solve this simultaneous control problem so that the same PD with the same OD with the same choice of the coefficients is able to bring all data simultaneously to their destination. This is, we say, this is ensemble or simultaneous control problem, okay? And this is a manifestation of the fact that this can be done. If you train, you solve the corresponding optimal control problem under these ansatz, you can see that indeed this can be done. The fact that this can be done was published in this paper with Domènec Ruiz-Vallet, who was in our team. Now he's an associate professor in Barcelona. Our SAR review paper 2 years ago, it said, yes, we can, right? So the statement of the theorem is very long, but actually it's very easy to understand. Yes, we can. You give me some initial data, you give me some targets along this ordinary differential equation, neural type. I can choose the coefficients so that all the initial data are brought simultaneously to the corresponding destination. This, of course, can be linked to optimal transport in the sense that the solutions of the ordinary differential equations are, of course, the characteristics of the corresponding transport equation, although here this will not be optimal transport in the sense of Monge and Kantorovich, but rather neural transport in the sense that the vector field is non-autonomous but driven by this neural nonlinearity. So the proof we did is by induction, and it's very much inspired on the way we solve the Rubik cube. So well, maybe some of you have, did anyone here ever solve the Rubik cube? I'm sure. Yeah, very good. How many seconds did you need? 120 seconds. Yeah. So 2 minutes. Yeah, okay, that's quite good, right? So what is the world record? I think it's like 5 seconds or something like that, right? So yeah, I saw someone solving it in 10 or 12, and it was quite amazing. But I mean, doing it is already, you know, challenging enough. But even for those, the majority of us who never solved the Rubik cube and will probably never be able to solve the Rubik cube, we know what does it mean. It means that this configuration, which is disorder, is well solved when we are able to bring every microphase to one single phase, which is homogeneous in color. And this is very much what we are, you know, willing to do. Take data, different colors, different labels, and bring each of them to a different region so that we can say data are well separated, they are classified. Okay? And then how do we do that? We hold the cube with one hand, while with the other we make it rotate. So half of the cube is frozen, half of the cube rotates, and we concatenate actions like this. And this is what I propose this method, this model does, right? Why? So now take whatever you are trying to classify, images in a very high Euclidean space, doesn't matter. One single data, one single image is a column vector living in an Euclidean space. This is in dimension D. D can be as large as you wish. You are classifying videos, so maybe the volume of the data is huge. Doesn't matter. We put it in a high-dimensional Euclidean space. This is a vector, right? So this vector evolves in time, and what I want to make sure is that, you know, at the end of the process, every video is in the corresponding folder. Classified maybe according to years, to, you know, to topic, to language, whatever, you know, the classification criteria is. Okay? So this is a column vector, x. This is the time derivative. Sigma is just a scalar. Sigma says 0 or linear. That's all. Now, what is a dot x plus b? A is a vector. This is a scalar product. V is a number. So a dot x plus b is what? is the equation for a hyperplane. Whenever you say a dot x plus b equals 0, you are carrying the Euclidean space into two halves. In one of the hemispheres, where this number is negative, sigma is 0, and this means that half of the space is frozen. While the other half, in which a dot x plus b is positive, sigma is linear. This is a linear differential equation, so it produces an exponential response, and the exponential response makes an evolution along in the direction of the vector field W. W is a vector. So in here, at any time t, you have d parameters in the column vector W, d parameters in the line vector A, and one parameter over there, 2d plus 1. Okay? And now, once you realize that with this kind of model, you can realize these actions like cut the space into two halves through along a hyperplane, keep one frozen and make the other move in the direction you wish, you can, for instance, see how the problem can be solved by induction. This is just an example in which I say, well, I have 9 points, 3 blue, 3 green, 3 red. They are all of them well classified except for one. Okay? So now I have to bring this blue dot to the blue area, but without undoing the good classification of the others. And I have to do it solving this differential equation in which I have to choose W, A, and B strategically. So I will do it according to a piecewise constant principle. And once I realize how I do this, you will agree with me that if there were more points, I can do it one by one, and therefore by induction prove my theorem saying in dimension 2 or higher, regardless how many data you give me and how many destinations, I can always bring the data set from one to another configuration by just using piecewise constant controls. Okay? So I will do 4 motions. You recall in each of the motions, with one hand I cut the space into two halves, and with the other I push the active part in the direction I wish. Left frozen, right goes up. Down frozen, up goes left. Up frozen, down goes left. And then finally, left frozen, right goes up. Okay? A posteriori, it's not so hard to interpret what we did. Let's do it again. So you see in machine learning, one of the keywords is backpropagation. This is, of course, very much related to classical control theory when you have the forward equation and the adjoint equation in the backward sense of time. This is also the dynamic programming principle of Bellman, who said, well, if you want to build optimal trajectories, you have to start from the end, not from the beginning, but rather from the end. And here we see what we did, right? So the whole effort was to make sure that this point, blue, will be the one to the right. Because if this blue point were here, it would be very easy to classify. I just cut here and I push the right part upwards. So the whole effort is to succeed making this blue point to be to the right from all others. And how do I do it? Well, it's very easy. The only thing I need to do is to make sure that I cut the upper half and move to the left, cut the lower half, move to the left. Oh, the problem is that the blue here is aligned with the green, and then the two of them will be together to the right, and this doesn't suffice. So to guarantee that this green also evacuates and is to the left, what I need to do is a first cut in which I just unbalance the horizontal orientation of blue and green, and then the rest of the process is done. Right? So if blue and green hadn't been in the same horizontal line, I could have done with 3 motions. I needed to use one just to make sure that they are unbalanced. Of course, if you use oblique cuts, you can even do it with 1 single motion. 2 single motions. You don't need 4. 4 is what you need when you do only horizontal and vertical, but of course we could do oblique cuts, and in that case you can do it with 2. Okay? So this is just to show you that there are some fundamental results in analysis and also in particular in control theory of dynamical systems that help us understand some of the clues of why these, say, neural networks, which are just graphs activated by this activation function sigma, are allowed to, you know, or are able to represent data. Now, maybe in the minutes I have, let me just jump a little bit to get to the last topic I wanted to show you. Because, of course, you know, we will not be that surprised about the impact of artificial intelligence if artificial intelligence was simply able to organize data. I mean, that's very helpful already. This is what you see in Excel, right? So you have an Excel table, and then you say, okay, organize data by this criterion, and then immediately, boom, like, you know, the email manager, you can say, okay, organize the email per alphabetical order or per date. That's very helpful already. But this is something we were already used to. Maybe what is more impactful of artificial intelligence is the fact that artificial intelligence is able also to generate realities that mimic, you know, are consistent with the one we are used to, but is able to provide new, you know, I didn't try, but let me, maybe we can do it online, right? So can you see? Yes, so I can say, write a poem about 40 mathematicians in Dortmund listening a boring talk on maths and AI on a rainy day. And then you see. So this is the generative capacity of AI. I mean, I promise I didn't think on doing that before, right? So if someone asks, well, but is really AI able to generate things? Well, you might like it or not, but here you have. I mean, and this is real time. And this is the first time this question was ever asked. I'm sure nobody asked ChatGPT this question before, right? Because there are some unique ingredients like Dortmund, rain, and so on. Okay, so rain and reason in Dortmund, 40 miles in coast of grey, gather in Dortmund a Thursday in May. Rain ticket, the windows, steady and slow, and formulas drip where umbrellas will go. And then you go to the end. So let it rain over Dortmund spires, over tired souls and academic choice. For even when talks grow weary and dry, mathematics dreams, and do so I do. So I don't know whether it's good or bad, but I mean the generative power is there, it's clear, right? I can, by the way, send you the poem later if you want to. So how does it work? And does this have anything to do with topics we might know in classical applied mathematics? Surprisingly, the answer is yes. So this is a joint work with our former postdoc, Can Liu, who is now a maître de conférence in Dijon, in France, in Bourgogne, right? So you might be familiar with. So this is a classical, I think the names are there. Is this written? Li-Yao inequality. There is a celebrated inequality for the positive. So Ivan is saying yes, he knows, right? So this classical inequality for the heat equation says, you give me any positive solution of the heat equation in any dimension n, then the solutions fulfill this inequality. The Laplacian of the log of u is greater than minus n divided by 2t. Okay, so this is a strange inequality, right? And the inequality is sharp. You take the Gaussian, you check, the Gaussian is saturating, the Gaussian fundamental solution is saturating this inequality. This inequality is related, of course, to, you know, to the classical semi-concavity in Hamilton-Jacobi. Although in Hamilton-Jacobi we do it the reverse, we take the exponential of u and not the log of u. is related to other inequalities for porous media, Aronson-Benilan, the one-sided Lütze's condition of Oleinik for the Burger's equation. There are many inequalities that are similar to this, okay? But this was, done in the context of geometry. This inequality was proved, okay? Now, what is the connection with generative AI? So now we are here, 40 mathematicians. We take 40 pictures. I would like to build a picture of a new mathematician, I want to generate new synthetic images of other mathematicians, right? So, by the way, generative AI does also this, right? So you know this this web page, right? Do you know this lady? Do you know this lady? No, of course you don't, because this lady doesn't exist. This other lady doesn't exist either. This man doesn't exist. So every time you click this web page, this person doesn't exist, is generating the image of a person that doesn't exist. But somehow it's interpolating images out of a data set so that, it's done in a way that, well, maybe if you observe very carefully, you will see any sign that this is not a real person. It's very hard to say, right? It's very hard to say. So how this is done? Well, this is done thanks to the heat equation. So how? Well, you take the pictures here, and you say these pictures here are just points in the Euclidean space where pictures are embedded. So you embed images into a Euclidean space of high dimension. We don't care, because we know how to solve the heat equation in any space dimension. This is the Gaussian heat kernel. Gauss again, right? And we know this inequality is true for any non-negative solution of the heat equation, regardless what the dimension is. So I take the corresponding empirical measure of the collection of pictures I have. I know what the solution of the heat equation is. It's going to be a combination of the Gaussians collocated at the corresponding places, very much like in Wiener, but now in a time dynamic manner. Otherwise, for a given time t, Wiener will say this is me, but no, this is Gauss. Okay, very good. And now, what people do is they say, okay, I take these pictures, I solve it forward, and now I try to come back along the heat equation backwards. And somehow, the warning is, be careful. We know that the backward heat equation is very ill-posed. And this is what precisely people use. They say, oh, but because it's ill-posed, the instabilities of the backward heat equation will be the ones that will be generating new images. So that's the principle, right? So forward is very robust, it's very stable, it's the Gaussian process. Backward is very unstable, but because it's unstable, let's use this instability to generate new images. Okay, time to finish? Okay, so now this is the trick. This is the only computation I'm doing. How do they do it? They say, I take the backward heat equation, it's ill-posed, but I can break the Laplacian into minus Laplacian into Laplacian minus 2 Laplacian, and then they write this minus 2 Laplacian as the divergence of u, gradient u divided by u. Well, this ends up being a Fokker-Planck equation, and when you look to the vector field over here, you realize that this vector field is the gradient of log of u, and then you say, well, what do I need in order to solve this Fokker-Planck equation? I need an estimate on the divergence of the vector field, and this is precisely the Li-Yau inequality. So the Li-Yau inequality says, when you are doing this forward-backward process, even though there is plenty of instability, this instability is under control, the backward problem is well posed, and therefore, when you launch the process, this is what you see. You start from an initial configuration of images, for instance, the images on this Leibniz kata, you do this forward-backward process, and then when you solve the backward stochastic equation corresponding to the Fokker-Planck equation, wherever the initial datum is, you immediately generate a trajectory that has the tendency to be attracted by the initial images. So that will not be sufficient, because this will be a manifestation of the fact that we are able to recover the initial images, but then we will be mimicking, will not be generating But of course, you can stop the process anytime sooner, and then you will be getting to other images that are close but not necessarily the same. And this is what generative AI does, and somehow explained through, these classical properties of the heat equation. This is the point I wanted to end just by claiming there are plenty of links between the classical topics and applied mathematics and the modern artificial intelligence and machine learning. Very often we are getting late in the sense that we explain why things work, but also there is plenty of potential through the understanding of the classical topics in applied mathematics like PDE, numerics, and control to contribute to new ideas that might, say, help to go to bring AI to the next stage and to make it more interpretable, more also respectful to, to human rights, energy, nature, and so on, and more efficient. Thank you for your attention.